we already explained the premixed friend based on their two important combustion characteristics. One is the flame temperature, the other one is the flame speed. And I try to emphasize based on the definition of flame speed, then you can identify the flame position for a given flow field for your combustion chamber based on the dynamic balance of flame speed with the supply velocity. The meaning on the dynamic balance for a given premise flame and a stationary sit at certain positions means there is some kinds of balance between the supply of a premixture coming from the upstream to be balanced with the consumption by the chemical reaction from the flame. And the burning intensity can be identified based on the flame temperature and also the flame speed, which means if you have a strong burning intensity, then the flame temperature will be high, and the propagation speed, the flame speed, is also high. And you should understand the burning of your premixtures actually is limited by the so-called dim limit and a rich limit. Okay, this is a friend. The limit is defined based on the available chemical reaction, which means the activity of the reactivity of your reaction of your mixtures is enough to support a flame or not. Okay, but there is another limit defined by the flame speed. We call this as a so-called the flashback or blow off. Your flame speed is much higher than your supply velocity, then this flame will propagate into your supplying source. That means they call so-called flashback. But if the supply velocity is much larger than your flame speed, then your flame premise flame will push away. They cannot stabilize in the given flow. Okay, this is the nature for premise flame we try to introduce in the beginning. But now we think about what kinds of influence or effect will be applied to the premise flame, and maybe they will suppress the burning intensity of premise flame, or maybe they will enhance its burning velocity. Now we are looking at from different point of view. One from the global combustion flow convection effect, and the second one we were dealing with the microscope point of view. That means that we are dealing the diffusion process. That means we try to think about the burning intensity variation, the variation on burning intensity on premise flame based on the change of flow convections or change in the diffusion process. Okay. The first one I want to introduce to identify the influence coming from the flow convections, then we call this a so-called flame stretch. The flame stretch is defined earlier by the Kalovitz, then we give a name as a Kalovitz number. What is the meaning of the Kalovitz number? They are dealing with a given flame surface area A. We assume we have a flame surface, this one, and they show you basically it's a control volume you have, and in this control volume you contain so many species inside, and they are react together, and they will produce some heat and release heat of combustion. And in these volumes, you can have a certain energy be contained in this control volume. Okay, this is a flame surface area you will have. But you think about it, this flame surface actually can be changed, right? You try to think about if this control volume is increased. When you increase the control volume, actually initially the thermal energy you have inside of your control volume is fixed. But when you increase your flame surface area, that means the heat energy, the energy you have inside of this control volume is reduced per unit volume, right? Because they need to redistribute to a larger volume. Now we say this A, this flame surface area is expand okay, is enlarged or be stretched. How can we have this kinds of increase, enlargement of your French surface? Because there is a flow, there is the flow velocity tangent to the French surface. As you remember, I mentioned for a given premixed plane, a planar premixed plane sitting in the counter flow or opposite flow or stagnation point flow, they are planar, right? But on the surface, there is a radial velocity coming from the jet, and they were tangent to your French surface. And this flow velocity will try to enlarge your French surface. In this case, they tell you the original or initial French surface is enlarged as the application of the tangential velocity. Now, this French surface increase, that means that they are stretched, and the burning intensity or the energy intensity will be reduced. When you increase this surface as much as possible, then you will find out the energy volume or the energy per unit volume is reduced to a minimum. Then you will reach to a so-called French extension, because the local energy density cannot support the chemical reactions continue proceeds, then French extension. So you will figure out the flow stretch coming from the tangential velocity on the French surface may be the cause for the French extension. This is the basic idea, and the columns give you the definition for a so-called French stretch factor, chi. Then the chi defined by this, okay? Chi means equal to, basically they are looking at the French surface A, right? This is A, but this A, the change of the French surface area, basically they can be described by many ways, because so many factors were applied to the change of the French surface area, which means when you try to describe it, you need to use the so-called total derivative from the fluid mechanics definition, capital D divided by capital T, right? And this is A. We are looking at the material derivative or total derivative of your French surface area. And in terms of the non-dimensional factor, Kalbitz number, we use you need to divide by original A, then the area cancel out, but there is a time units. You need to have a Peeting zone and French speed as a time as a unit time for our non-dimensionalization. Then this chi will be a non-dimensional value. Okay, this is the first point I want to define. How can we evaluate the strength of stretch on the frame, and what is the effect? And I will give you several examples to tell you how to describe it. Let's go to the slides. I can show you some example. Okay, now this is a very nice examples I want to show you. Let's look at the so-called material derivative or total derivative. If you think about how to evaluate its value, you need to know the function of the total derivative or material derivative. But anyway, now we try to go back to our the ideal definition. We are talking about the adiabatic flame temperature or a definition of French speed. Basically, those kinds of concepts is initially defined by a so-called a planar stationary frame propagating in an one-dimensional steady flow. You remember I plotted those flow structure for the one-dimensional planar frame, right? The planar frame sits at the origin, and the coming premixture support the burning of your premixed frame. Then this frame sits very nice, and all the flow will move through from the upstream and passing through the frame, then go to the downstream. Okay, this is a one-dimensional model. Now we try to think about how to describe all those kinds of convection effects onto this one-dimensional flow, because we try to look at more realistic different propagation in different systems. Now there is some important factor need to be described based on the mathematic formulation, and those formulations described by material derivative here. Capital D divided by capital T means the definition is partial T plus velocity vector dot product, right? If you have an A, you put your quantity A into the this function, then you need to think about all the function get involved, and you write it down as the x, y, z coordinates with t. Then they tell you, okay, those kinds of derivative involved is there is different kinds of partial derivative. The first one you can see there is a partial t representing the unsteady effect. What is the meaning of? You need to consider the unsteady effect. Here, this unsteady effect basically relates to the so-called original, we assume stationary frame, right? The premixed frame sit at a certain position without movement. Okay, but now when you think about if this frame is moving, okay, now you need to think about the frame surface vary depends on the time. You need to think about the partial A, partial T. Okay, this is the first point related to our original assumption for one-dimensional premixed frame. The next one you will find out. Look at the second term. This is a flow velocity, right? Usually for our one-dimensional flow, there is only one velocity along the coordinates, and then this flow velocity is just normal to the frame surface. But in reality, all kinds of premixed frame exist in the three-dimensional flow structures, which means the flow velocity, if you have additional flow velocity, for example, the stagnation point flow or counter flow, you figure out there is the radial velocity tangent to your frame surface. Then you need to think about the velocity field you may have. Then you go back to think about when you need to think about the two-dimensional flow, three-dimensional flow. Then those kinds of consideration is additionally it need to be modified through the previous one-dimensional model. This is the second point. You can figure out the frame surface A vary with your flow velocity field in two-dimensional or three-dimensional flow structures. And the last one here, you can see the term capital the velocity vector dot product means there is some velocity component times the quantity vary with your position, right? This is a partial x, partial y, and a partial z. That means that you may think about your your surface, your frame surface will change along with x coordinate, y coordinate, and z coordinate. That means that your premixed frame should not be a planar, a flat frame. They may be curved and with different kinds of geometry exist in different kinds of coordinate system. Okay, which means when you're dealing with the so-called material derivative, actually you are talking about the time dependence, space dependence, and also flow velocity get involved. These three factors actually can be reflected to think about the modification on our original one-dimensional model, and it is very nicely described based on very simple experiments in our laboratory. Then you will figure out those kinds of three kinds of premixed frame. I will introduce much soon, used for a long time to describe or to examine different kinds of burning characteristics for premixed frame. The first one I try to give you basically is you are quite familiar with is the Bunsen frame, right? The Bunsen frame actually you can think about the frame how the change of frame surface in the Bunsen frame. This is a real Bunsen frame. Maybe we just look at the rich premixed frame inside of this double frame. Actually, this picture is corresponding to 14% methane premixed friend. Okay, now you think about when you go from the base or your premixed friend, that means the excipient or burner, and then you try to look at the friend surface. Okay, the friend surface on the friend cone. Okay, this is a circumferential friend shape. And initially, you can see there is a larger radial distance, right, away from the center line. That means that when you count the friend surface near the base here, you can see there is a larger friend surface. But you go through, when you go through the actual directions, follow the central line, you will figure out the friend surface. Try to the circular friend circumferential friend surface is continuously reduced when you move to the very close to the tip of your Bunsen premixed friend, right? At this tip, actually, the older friend surface will reduce the minima value. Okay, they almost concentrate and club together to a single point. Now, if you understand these kinds of variation, they tell you along the center lines, when you change your actual coordinate system, you change your coordinates, move from the base of your premixed friend to the tip of premixed friend, the friend surface continues reduced. Okay, these kinds of reductions actually influenced by the so-called the friend curvature. Actually, there is partial x, partial y, partial z, right? Along the x, if you assume x is the actual coordinate system, they tell you if you put a friend surface here, they tell you this friend surface is continuous change along with the actual coordinates. Now, this will tell you the inference coming from the so-called one of the example, the friend curvature. They tell you your friend surface will change along the movement of your actual coordinates, and it up to move to the tip of Bunsen frame. In this sense, you will see partial A, partial X actually is continuously reduced, right? The partial A, partial X, along the X, A is reduced, then you can see the friend surface is reduced. When you have a reduction of your friend surface, that means you force your original energy will restrict in a small volume of your control volume. That means the energy intensity will be increased, right? And in this sense, we say this friend the variation of friend surface is under compression. Okay, because initially we define the Kalowitz number, we say the friend is under stretch. Under stretch means the friend surface initially is small, then they will become larger and larger. Then this basically describing the so-called stretching. Is a stretching. But in our case, the Bunsen burner, Bunsen friend, they tell you the friend surface is continually reduced, which means they show you a so-called a negative stretch. A negative stretch is equivalent to the idea about the so-called compression. Okay, and this compression will give you the idea the burning intensity or energy intensity inside of your friend surface will be enhanced. Okay, this is the first point you can see from the physical descriptions. Now the next one, we think about how to explain the influence coming on the stationary contrary to the movement. That means the friend surface will change with respect to time. Okay, this is an unsteady friend, and we are looking at the friend movement. There is a simple experiment you can figure out. So many experiment reports give you the idea to see how the ignition of your premixture and to tell you they can generate the spherical frame and to let you know the propagation of the spherical frame. And this is a typical example I tell you. There is when you look at this, there's A, B, C for different concentration for methane premixtures, and by different equilibrium ratio. In this row, there is equilibrium ratio equal to 0.33 is a linkage, and this is equal to 1.01 is under stoichiometry, and the last row they represent the 1.74 is a rich case. But you don't care about the detail, the burning structure. I just want to let you know how the flame propagates from the small ball to a large ball. Okay, you can see for different equilibrium ratios, so when you ignite it, okay, this in the whole system you contain a certain amount of the mixing premixture in, then you use the spark and ignite it at the center. Okay, there is a spark ignition occurs, then you produce a small spherical ball very nicely, and this ball will extend, right? Will extend to, as when you go to the from the initial time 3.11 millisecond, then go to the 12.44 milliseconds, 44 millisecond, and you can see the size of your the propagation ball become larger, right? Okay. Now you can see originally your flame surface is a small spherical surface, but now for the next instant, then become larger, flame surface is increased. When you have an increasing surface, that means this flame surface is under stretching, as we described from the definition for Karovitz number. Then that means this flame is under so-called positive stretch. And this is a typical example. I tell you the expanding spherical flame is under positive stretch. This is has an opposite effect compared with the previous compression behavior on the Bunsen burner. Okay, Bunsen flame, the flame is under compressions, then the energy intensity will be increased to a small volume. But for the spherical expanding flame, actually the energy will be distributed for larger flame surface. The energy density is reduced for a larger flame surface. Okay, and the third one, we are looking at the third point because where I just mentioned, for idea one dimension flow, the flame is just experience the normal velocity coming from the premixtures. But for reality, actually they will experience, for example, we just mentioned, for the opposite flow, when you have two identical premixture impinging together and then you ignite it, then you can have a so-called double flame, identical double flame sit here, and they can stabilize in this opposite flows. But you understand there is the radial velocity acting on the surface, tangent on the surface. That means the flame surface originally maybe you take a control volume near the center line. Originally you set the control volume like this. Then the next time interval, since the flow is moving along the surface, then they will extend to a certain extent, which means a small volume to the larger volume. Flame surface is increased, then this one still tell you this premixed flames under positive stretch, and this caused by the so-called flow non-uniformity. The flow non-uniformity actually means this flame experience not just the uniform axial velocity only. There is also has some radial velocity tangent to the flame surface. Okay, originally you will have a complete uniform injection velocity at the exit plane of your burner, but those flows will distribute their axial momentum to the radial momentum. That means that they have additional radial velocity in the flow structure. Then we cannot say the older flow has a uniform velocity because they have a change. The uniform velocity profile has a very good non-uniformity, only occurs in the potential cone of your jet burner. Remember, in the potential cones, okay, every point, every flare, the axial velocity, they only have axial velocity, and those axial velocity is equal to the injection velocity of your burner. Okay, but now these three examples just give you the idea to tell you the flame surface will be changed even in our laboratory experiment. For example, the Bunsen burner premixed flame, the expanding spherical flame, and also the opposite flame. And we try to look at those kinds of inference coming from the flow convection. I give you the example. The typical one is the opposed jet frame. Okay, now I try to give you some idea to think about how a given premixed frame experience different kinds of flow stretch. Okay, now as you remember, we already have some estimation and analyze a theoretical analysis on the flow structure for a given opposed jet flow, and I think you are familiar with these two plots, right? We have a very good agreement between the theoretical petitions and experimental data, especially when you get involved with mass diffusion near the stagnation point, then we have a perfect agreement on experiment and numerical results. But I give you the simple description here. The left-hand side represents the actual velocity distributions along the different actual coordinates. And here, the right-hand side represents the radial velocity variation along with the actual coordinates. Okay. Now, for this experiment, actually, we fix the injection velocity of a double jet. Okay, and they are equal to around. I remember maybe I did this experiment very earlier, 30 years ago, but from the plot, I think this is around 46 centimeter per second. Okay, this is coming from the x plane of your burner z equal to 0. We put the origin at the x plane of the loader burner, and 20 second z equal to 20 second. That means the age of the x plane of the upper burner. The separation distance is just equal to 22. Okay. Now, if you have a flow, the loader flow with the injection velocity around 46, then you can see this is the variation of actual velocity profile. They were approaching to 0 because the flow basically has two identical jets impinging together. Then here, this is z equal to 11, just half of them. Your stagnation plane exists here. Okay. Now you try to think about this is cold flow up, okay? Now, if you applied the premixture of your mixing mixed with the air into your burner, you will think about original. You may think of you can have a stronger. For example, you try to choose the stoichiometric conditions. Now, this premixed frame may give you, okay, suppose the frame speed is around 40 centimeter, okay, here, then you will expect the location for your premixed frame exists in this flow, maybe in here, in this position, right? Because this is the initial point at the exit point, 45 centimeter per second is equal to injection velocity. When your frame speed equal to 40, then possibly they will exist here. But in reality, actually, you will find out there is a slightly shift, but very close to this position. You can do this kind of estimation. The premixed frame is with the 40 centimeter per second frame speed may sit here. But now, when you change your concentration from the stoichiometric 9.5, maybe you change it to the 8, and the frame speed should be reduced around 36. Then you will figure out the premixed frame may sit here a little bit away from the burner, right? And then you continuously reduce your burning intensity by change your mixing ratio. Maybe now you go to the 7%. Now you can find out the frame speed for 7% mixing ratio. Then I just have a 30 centimeter per second as a frame speed. Then you can estimate the frame location may sit here. Okay. By this kinds of change on frame speed, you will figure out your frame, the location of your premixed frame may change from the position 1 to position 2, position 3, which means when you reduce your mixing ratio to reduce the burning intensity, frame speed is reduced. When you have a lower frame speed, that means that your premixed frame will sit far away from the exit plane. They will move to the stagnation plane. Okay, when the flame speed becomes smaller and smaller, the only way they will move to the stagnation plane, because the local flow velocity becomes smaller to fit with your smaller flame speed. Okay, this is the first idea you need to know when you do the experiment. You can have it when you do the measurement for the cold flow. Now the next step, you try to initiate the flame propagating in your flow. You need to figure out when you generate a stronger premixed flame, then this premixed flame will sit closer to the burner. But if you try to set up a weaker premixed flame, this flame may sit closer to the stagnation plane. Okay. Now, when they move to the positions closer to the stagnation plane, what's happened? Let's look at, we bring the position of 1, 2, 3, 1, 2, 3, right? We move to the downstream side, position one closer to the burner exit, position 3 closer to the separation, to the stagnation plane here. Okay, 11. Now, when you have a flame sit a little bit to the downstream side, for example, for the position 3, you look at the from 1 to 3, you can find out they may experience different strengths of radial velocity, because from our low flow, cold flow measurements, you find out when you increase your actual coordinates, actually the radial velocity increased. When you have a strong radial velocity, that means for a given time interval, the boundary of your flame surface will increase to a larger extent, right? That means they will experience higher flame stretch. And usually when you do the experiment, for example, you try to identify or given premixtures and to look at the extension limits. Okay, I need to tell you I already mentioned there is the so-called, for the burning, there is a two limit. One limit is so-called the friend limit. The friend limit or non-infinite limit basically defined by the reactivity of your premixture. Reactivity means the ability for chemical reaction. Okay, because in the reaction process, they will release heat of combustion, and this heat will support the continuous chemical reaction. The reactivity will be described by the infinite limit or from the limited limit. And we get rid of also all the influence coming from the surrounding. Okay, but for extension limits, there is different story. Extension limit means, for example, maybe you have a 9.5% premixture, and definitely this is stoichiometric premix, right? Premixtures, then you can burn it because burning intensity is very strong. But if you put this flame in a circumstance with very large heat loss, you can find out this flame cannot survive, because there is some heat coming out. Okay, those kinds of heat loss will produce, even you are very strong, 9.5% mixing ratio is you can produce a strong premix flame, but the heat loss coming from the outside is large enough to carry out all the heat combustion you may release. Then this flame still cannot survive. Okay, then we call this as an extension limit. Extension limit is influenced by the outer surrounding, different kinds of effects. Okay. Now, when you look at this, we try to think about, if you try to do the experiment, for example, here, you now in this flow, you have an injection velocity around 46 centimeter per second, right? Now you pick up a mutual condition. For example, we just mentioned maybe 6%, or maybe, I'm sorry, we start from the 9.5. Okay, 9.5%. We assume 9.5%. Okay, 9.5%. Then you can generate the first frame here. Okay, now you try to reduce the concentration of your mixant, but keep the injection velocity the same. Okay, that means the supply velocity the same, but concentration is reduced. That means that now when you reduce the concentration from 9.5 to 7, that means the burning intensity reduced, flame speed reduced. Now the flame will move to the position 2. Okay, you further reduce the concentration mixing ratio to 6. the flame speed is reduced 2, then the flame move from the position 2 to position 3. Then you try to reduce the 6% a little bit, and then you find out actually when you reduce the mixing ratio lower than 6, maybe 5.9, you will find out the flame disappear. You cannot generate a flame exist here. Then we identify in this flow, the extinction limit for premixed flame is around 6%. Okay, 6% is higher than original defined from the living limit. For the methane is 5%, right? But now here in this experiment, you may experience the extinction limit is 6%. That means that your mixing ratio should be higher than 6. Otherwise, your premixed flame cannot survive in this flow. What's the reason? Actually, this is very clear to let you know, because for the 6 or 5.9% of methane flame, they will experience certain amount of flame stretch. This flame stretch has an outer influence to your stabilization of premixed flame. Sometimes they will give you because we increase the flame surface, right? That means that you dilute your thermal energy to a large area, then this will give you the imbalance between the thermal energy and chemical energy, and they will produce they cannot perceive the chemical reaction, then the flame cannot exist. If in this case cannot exist, cannot survive, that means the flame extinction. Okay, by this kinds of experiment, you can identify in such a system by a given, especially this the important thing is in this case we have a given injection velocity is a 46 centimeter per second. Now flame extensions for methane premixtures around 5.9% and an extension. This is the very nice experiment to tell you for given premixed flames with mixing ratio under 6%, they cannot survive in this flow, okay, because they experience flame stretch in the flame stretch caused by the radial velocity tangential to the flame surface. Okay, this is always this is a good idea to examine the extinction limit for premixed flames by using this system.